We've already started talking about asymptotic growth of functions. We talked about last time, we talked about O notation, and we also started talking about omega notation. I have a little bit more I'd like to talk about for omega notation, and then after that we will learn about theta notation. So that's where we're going here in this lesson. Let's start by reviewing just a little bit about what we talked about last time. After learning about what O notation means, we also then found out this fact, that it turns out that a polynomial function of degree k is always going to be O of n to the k. So basically what you get to do is, if you have a polynomial function, you get to just take that term with the highest degree and drop the coefficient in front of it, and then you can say it's O of what's left. Okay, so we had some examples here. Here is a function, and you see that I've written this function is O of n to the fifth. That's because 5 was the highest exponent there, and so we could say it's O of n to the fifth. Here, this one, I meant to have a 2 on this second n. So I wanted to have a 3n squared, and so there's a 3 there instead. But anyway, that again is a polynomial function, so we would be able to say, we'd find the term with the highest degree, and the highest degree is 3. We can just drop the coefficient and say then that that polynomial function is O of n to the third. And this one would be O of n squared. Now, if we have something like this with no exponent on the n, you know that officially there is an exponent there, and it's to the first power. So anyway, we would say that that function is O of n to the first power. So after learning that fact, we learned how to prove that fact. Remember, in order to show that f is O of another function g, we need to come up with a c and an n naught to show, to prove that for that particular c and that particular n naught, c times g is going to end up being greater than or equal to the function itself, the function f, once we get past that n naught. So we learned that if we have a polynomial function of degree k, then these are the two values that combine to work as a witness. N naught would be 1, and c is the sum of the positive coefficients. And we actually showed how to prove that for individual functions. So how to actually show how we end up getting c, and be able to then show that any given polynomial function is that particular O of something. Okay, so remember what we talked about, and this is again a review. We said that if you have some negative coefficients, then you're going to drop the term with the negative coefficient. So we're going to drop that negative 3n to the third coefficient. And if we do that, then what we end up with is only going to be bigger, because we're not subtracting that positive value out. So we can put a less than or equal to sign right there between the function itself and then this new function after we've dropped that term with the negative coefficient. Then, but besides that, then we do what we did before. We've talked about, remember, we kind of pumped up the powers of n so that all of the terms have the same power, and it's that highest power, in this case 5. And again, that's only going to be bigger either equal to if n is 1, but once we get past 1 and get higher, then it's going to be greater than. So again, this new expression that I have over here is going to be greater than the original function. And then once we pump up those exponents, then we can combine the like terms. And so we would here get 12n to the 5th after adding up the 3, the 7, and the 2. And so, but 12n to the 5th it's a multiple of n to the 5th, right? So we could say that f of n is less than or equal to 12 times n to the 5th as long as n is greater than or equal to 1. So that would mean that f is O of n to the 5th. And we would say that c equals 12 and n naught equals 1 are witness to that fact. Notice c did end up being the sum of the positive coefficients in that function, and n naught did end up being 1. So that statement above tells us how to find n naught and how to find c, and if that's all we care about, then that's all we would need. But I do want you to be prepared to be able to go through this little proof like this. Then we started talking about omega, and we said that that this statement that you see here on the screen is true, that if we have a polynomial of degree k, then f will be omega of n to the k. And that's true if the coefficient of the n to the k term, the term with the highest power, if that's positive. So if that coefficient is positive, then we know that this is the case. This is because we're being told that. Later, we'll talk about how to go through a little proof and actually find a c and find an n naught. But for now, we're just going to take this as true and then just look at some different functions. So here's a function starting out. The highest degree is 5. So, and the leading coefficient is positive, so we know then that this function would be omega of n to the 5th. Here we would know this function is omega n to the 3rd because that's the highest power. Here it's omega of n to the 2nd, and here omega of n. So we're just taking that statement as being true and then just being able to go straight and find and be able to say that, how we can use make these statements involving omega. Now, it's not true when, as we said, it's not true when the leading coefficient is negative. Here's an example here of two functions, one just being x squared, and well, you can see the x graphs over here, but we'll be talking about a function in terms of n since we're in the discrete situation. But if we did go into the continuous situation, you'd see what we have here in the picture. And you see that the blue would be the f that we're looking to see if a multiple of g could be a lower bound. But we see that that's never going to happen here because look at what f is. It's a parabola that's opening down, and so as n gets bigger, it's only going to get further and further away, and there's no way that any multiple of the green would ever be a lower bound. So it's just not true. We won't be able to say it's true that that a polynomial of degree k is omega of n to the k if that leading coefficient is negative. Now, we just learned that general rule, but what if we want to just check that out for ourselves? Let's see if we can do something algebraically to prove to ourselves that in this case here we have a function of degree 2 with a positive leading coefficient, and then we have g, which is just n to the second power. And let's see if we can prove algebraically that f is omega of g. So we'll start out with just the function itself. And remember, now that we're talking about omega, we're going to be wanting to find functions that are smaller than f to be, than f is, because that's what omega is, the lower bound. So here's what we can do. If we drop these two, the two extra terms, 2n plus 1, and we just look at this first term, we see that, yeah, just using the first term by itself, that would be smaller than what we started with, because dropping a 2n, that's positive, dropping a 1, so I'm getting just smaller. So I can say that this relationship is true, that the function f is greater than or equal to, I'll say or equal to, although we know it's officially completely greater than, but we'll just say greater than or equal to, because that's all we need for the proof for omega. Okay, so we can just drop those two terms. Now we can only do that if we don't have negative coefficients there. Okay, so we'll kind of learn in a little bit how to handle if there are any negative coefficients, but assuming everything's positive, we just drop those extra terms. Okay, and so we can say it's greater than or equal to 3n squared. But that is the very definition of f being omega of g, right? Because f is greater than or equal to a multiple of g for any n greater than a certain amount. And we saw that this is true for n greater than or equal to 1, so we can say that that would be that n naught would be 1 here. So, we did it for that example, but here's what we're going to be told. This general rule here, that where, just like we did before with the with looking at the polynomials of degree k and finding the relationships with the O notation, we're going to be given just the bottom line. How do you, what do you come up with for C, and what do you come up with for n naught to show that what we've just said is really true? Well, if you take a look at what we just did in that example, you notice C ended up being the coefficient, the leading coefficient, the coefficient of that term with the highest degree. Well, that's what we could do for any polynomial function as long as f doesn't have negative coefficients. So turns out that we can always use, in that case, we can use C as being that leading coefficient, and then n naught will always be 1. So those are what we can use as witness to the fact that that polynomial of degree k is really omega of n to the k. So here we've done the little proof where you saw it done algebraically, and then we're given just the fact that, hey, this is true for any polynomial. You can just use this c and this n naught, and it will always be true. But you can see this is an easy enough little proof up above that you could do that for anything if you were asked to show it. But what if f has some negative coefficients? So remember, before we were able to do that little proof easily by just dropping some of those terms. But here, if we've got some negative terms, we can't drop them and then say that the result is going to be, smaller. And that's what we need to be able to say for omega. So we have to follow this, might be a bit of a complex, it's not that bad, but it looks a little complex at first, where they're just going to give us a rule, okay? And they're just going to tell us what we can use for C and what we can use for n naught. And as you can see here, it says that the choices for C would be, the choice for C would be that leading coefficient divided by 2. That's again if we have these negative coefficients there. So we're going to take that leading coefficient, divide it by 2, and then n naught's not going to be just 1 all the time, which it always has been with everything we've been talking about with these polynomial functions. N naught has always been 1 in the past, but now it's going to be either 1 or another number based on whichever one is biggest. This other number, you see, it's the maximum of 1 comma and then 2a over a sub k. But what's a? Well, you see up here it says a, let a be the sum of the absolute values of the negative coefficients. So what you need to do in order to come up with a C and an N naught in this case, where you've got negative coefficients, not the first term though, remember, because that first term can't have negative coefficient, or we won't be able to say it's omega. But if we've got some negative coefficients, then this is what we use. So we'll first of all find A. Okay, so let's go through this example here. Well, sorry, I see here I'm finding C first, and C is the easiest one. So let's go ahead and find C. So C is that leading coefficient divided by 2. So in this case, C is 3/2. Now, how are we going to find N naught? We have to first find A. And it says, let A be the sum of the absolute values of the negative coefficients. So we've got a -4 and a -2 as coefficients. We want to add their absolute values. So we're going to have a +4 and a +2 gives us a 6. But now we want to take 2a divided by that leading coefficient. So we're going to have 2 times 6 divided by 3. 3 was the coefficient of that leading term. And so that ends up being 4 in this case. Now, once we find that 2a divided by a sub k, we have to decide if that's bigger than 1 or not, because N naught is the maximum of either this number we just found or 1. So in this case here, if we're looking at 1 and 4, the maximum is 4. So we will have 4 as our answer for our value of N naught here. So this is what we would say here for the witness to the fact that this polynomial is omega of n squared. We'd say C is 3/2 and N naught is 4. Now, we're not going to end up having to go through some algebraic proof on this category of functions, okay, on this category of polynomial functions. You're just going to need to know these values and be able to, given a function and then given g, which would be that something like n squared in this case, or n to the 5th or something like that, you're just going to need to be able to come up, find C, and find N naught by using these formulas here. Now, since your tests will be, your tests will be online, and since we're remote and I won't be watching you take it, I'm not going to keep you from using notes. And so this is a kind of thing you might want to just write down somewhere on a little cheat sheet kind of thing. You won't be cheating, I'll just call it a cheat sheet though, as something that you might not have memorized, but that if you need to use it at any point, it would be available for you. So you might want to start writing a few of those things down that you think you might need when you that things that you might not have memorized, that you might want to be able to look up quickly when you're taking the test, and this would be one of those. So this summary then talks about how to show that a polynomial of degree k is omega of n to the k, as long as the coefficient of that leading term is positive. And remember, there were two categories. One is that there were no negative coefficients, and one that where there were negative coefficients. And so what we've just said, those two methods for coming up with C and N naught, we've already talked about, but here they are all on one page. So that would be something else you could print off or something and know that you could look at that quickly and easily if you had to show, come up with those witnesses for showing that a polynomial function is omega of something. Now, finally, we come to theta notation. And don't worry, once you get O notation and omega notation down, this one's pretty easy, okay? So again, we're going to be looking at two functions and comparing them, and we want to know, is f theta of g? Well, here's how we know if f is theta of g. If f is O of g and f is omega of g, then f is theta of g. So as long as we've proved those two, it's O of g and omega of g, then we say, okay, it's theta of g. Now, in other words, let's kind of write this in, say this in a few different ways to kind of help it make sense. In other words, if we can find a constant c, where that c times g is an upper bound, right, because that's the O notation part of it, and another constant, I'm going to call it k just so we don't get the c's mixed up, another constant k, where k times g is a lower bound, that's the omega part, then we can say that f is theta of g. And basically what then this is saying is that we would be able to say that that g and f kind of have the same, kind of are shaped the same in their asymptotic behavior. They kind of have that same rate of growth. And remember what I had said is we were first looking at these upper bounds with the O notation, and we were saying, yeah, but an upper bound doesn't really tell us too much because we could have some function that's way higher than our f. But I said what we're going to now do is talk about lower bounds, and then we're going to try to squeeze them together to get something where we would then be able to have a function that we're saying is shaped similarly and that has the same asymptotic growth. And so this is what we've done right here. We've, noticed these are two different constants. We found one constant so that the multiple of g was an upper bound, and found another constant so that the multiple of g was a lower bound. And so then because of that, we say, well, then they must be shaped similarly. So we're going to say that f is theta of g. And if we have f being theta of g, then we would say that f is said to be the order of g. So f is of the order g. Now, if you remember what we've just talked about, we've already been shown that a polynomial of degree k is going to be O of n to the k. But we also just learned that a polynomial of degree k is omega of degree k. So, by definition, we would be now able to say that a polynomial of degree k is theta of n to the k. Now, only, of course, we have this one caveat here, that leading coefficient can't be negative. Okay, see that negative, that leading coefficient a sub k has to be positive, because remember we saw it wasn't a problem for finding an upper bound, but it was a problem for finding a lower bound. We found that it's just not, f would not be omega of n to the k if we have that negative leading coefficient. So we're going to make that statement that let's as long as our leading coefficient is positive, then we can say that polynomial of degree k is theta of n to the k, and therefore shaped similarly as we get large with n than n to the k itself. So here we go. If f is equal to 3n squared minus 4n minus 2, then we've already learned that f is O of n squared, and we've also learned that f is omega of n squared, so we can say that f is theta of n squared. And another way we would say that is f is of order n squared. Here we've got this function. We know that f would be O of n to the third. It would also be omega of n to the third, so f is theta of n to the third, and we would say that f is of order n to the third. And here f is 3n plus 1, and we'll forego the O and the omega because now we know that's true, and so we could jump straight to the theta and say f is theta of n. And here we would say f is theta of n to the third. Some functions don't even depend upon the input. So if we have f of n equals 17, that we call that a constant function, and it does not depend on what n is. It's always going to be 17. That type of function, a constant function, will be considered theta of 1. So we would say it is of the order 1. Hopefully now you understand that concept of theta, and you're well aware that there are functions, all functions grow at different rates. So you see here we've got some functions that don't grow very quickly at all. Others grow very quickly, and they continue to grow quicker and quicker as n gets large. Well, so we have this classification system in a sense, now that we've talked about theta, but it'd be nice to put it together in a table so that we can kind of look to get an idea what type of functions grow quicker than other types of functions. So if we take a look at this table over here, these are some common functions, and over to the right you see we have a constant function, some different ones. Eventually you see linear functions, quadratic functions, and so on. So those are the names over on the right. On the left you see the theta notation for those, and these are in a specific order. So they're ordered according to the rate of growth. So it starts with the constant function that does not grow at all, and then it gets more and more, growing a little bit more, until we get up to, we've got the quadratic, and then we've got cubic that grows quicker, exponential, where the n is actually in the exponent. Then that grows even quicker, grows pretty quickly. But then here's another one that grows even quicker, and that's n factorial. So you will always have this chart to refer to if you're given two functions and you need to know which one you would say grows quicker. We would be able to find out by knowing the further down in the chart it is, the quicker it would grow. One thing they don't have in this chart is they have the quadratic and the cubic, but what about when we get larger values like n to into some other number like n to the 1,000 or n to the million? How would that relate to these others down below? Would they, if k, which again k is just the constant and does not it's the n is being taken to this power. But if we get big enough for k, though, would that overtake these last two on the list, exponential and factorial? But the answer is no. No matter how big we get for k, it's going to go in this list here. Now, as k gets bigger and bigger, we go down the line, like you see how n squared is above n to the third, and then n to the thousandths would go down here. And so the bigger that exponent is, the further down in the list it would be. But it won't overtake the c to the n or the n factorial. These grow even quicker. Unfortunately, we don't always have functions that are very simple, like all we have is a term with, a polynomial function, or, maybe we have more than just a exponential expression in the function. Maybe we have a combination of them. Maybe it's a sum of different kinds, like maybe we have f of n equals n squared plus log of n. So, when we've got two together, we need to learn how we can classify them when, when there's not just simple as what we saw in the previous slide. So we've got some rules for asymptotic growth of functions so that we can use when things get a little bit more complicated. First of all, the first one, we're still talking about two functions, f and g. If f is we're talking about f and g and we're comparing them, but we're going to be also looking at a third function called h. Okay, so we're saying if if f is O of h and g is O of h, so we've got two functions that are both O of h, then this rule tells us that if we add f and g together, it's still O of h. Okay, so if the two functions are O of the same function, then the sum of those functions will also be O of that function. Now, here's one that involves omega, and this says if f is omega of h or g is omega of h, then the sum is omega of h. Now, the difference here is we're talking about omega, and you notice there's that or word in here instead of and. So we don't have to have both f and g satisfying this. We only need to have one of them satisfying the omega of h. And if only one of them does, then we can say that the sum also is omega of h. We're going to be seeing examples coming up. So I know right now all of this together might seem like a lot, but we're going to do some examples and look back at this little list of rules and then see, kind of work with them for a little bit. Okay, here's another one. If f is O of g and c is a positive real number, then c times f is O of g. Basically saying we can take, if f is O of g, then we can take any constant of f, and it's also O of g. Here, same thing with omega. If f is omega of g and c is a positive real number, then c times f is omega of g. So we take constant times positive constant times some function that does not change this fact that it is omega of this other function if it started out that way. Here's one that you have to read carefully to see, how is this different than that one at the beginning. The one at the beginning, we had f and g, and each of those were O of h. Well, this one's different. We've got f and g and h, but I kind of, I think of it, and it's not really this way, but I kind of think of it as like that transitive property where we've got f is O of g and g is O of h. So f is O of h. So you see that, see how this is different than that first one. We're not saying both f and g are O of h. We're saying f is O of g and g is O of h. Then we can say, if that's true, that f is O of h. And we have that same thing for omega. If f is omega of g and g is omega of h, then f is omega of h. Now we're going to look at some functions that involve more than one type of basic function in each function itself, and use these rules over to the top right and see if we can answer some questions. Also, you see I do have that chart there so that you can kind of remember which functions grow quicker than others. So first of all, here we've got f. F is 5 times 2 to the n plus n plus 3. So the question is f omega of n to the 1000? Okay, so we've got to think about this. Is it omega of n to the 1000? Now, if it was just if f was just one basic function, like it was just this first term, we could look at the chart and see, does that term grow quicker or less quick than n to the 1000, and then answer that. But we've got these three terms here, so we have to kind of go and look at something over here on the right that has to do with omega here, and recall the second one says if we've got two functions f and g, and either if one is omega of some other function or g is omega of some other function, then f plus g will be omega of some function. So that means that either f or g has to be omega of that h, but not both of them have to be. So if we take a look at this, and remember we're looking at f here, is f omega of n to the 1000? It is, and why? Because of that second one, because is either of these terms omega of n to the 1000? Now, what does it mean to be omega of n to the 1000? That means n to the 1000 would be a lower bound, that it would grow, that something over here in f would grow quicker. Well, it turns out this 5n to the 2 to the nth, that you see down here, the exponential function here, it grows more quickly than even n to the 1000. So because of that term, we would be able to say that one of the terms grows faster than n to the 1000. So yes, since one of them is omega of n to the 1000, then we'd say that the sum is also. Next question, h. Here we've got in h we've got two terms. One involves log, which is kind of interesting, but that does show up on the chart. So there's some examples like this. And then another one, n log. And the question is h theta of n squared? So remember what theta means. We've got to prove that h is O of n squared, and it's also omega of n squared. But here we see that these are log functions. And if you take a look in this chart here, these log functions, the log, and even the n log, those don't grow as quickly as n squared does. So we would not be able to say that h is omega of n squared. And that would be our only hope in eventually showing that h is theta of n squared. So if we can show that, h is not omega of n squared, and we can, then we could say then there's no way it can be theta of n squared. And again, the reason why we know it's not true here, that h is not omega of n squared, is that n squared grows quicker than either of those functions that are in h. So h together will not grow as quick as n squared would. Okay, third one is f O of n factorial. So let's look at f. We've got three terms here, and we would need to show or need to know that n factorial grows quicker than either than each of these terms, right? N factorial, if you look down here, n factorial is the one at the very bottom. That's the one that grows the quickest of all. And remember, to be O of n factorial means that n factorial needs to be an upper bound. It needs to be at least as big or higher. A constant times that, a multiple of that would need to be grow at least that or quicker. No, be above that on the chart. So anyway, we take a look here, and in this case, F, all three of those are O of n factorial, because n factorial grows quicker than 5 times 2 to the n and 3. So since it's true O of n factorial for each of those terms, then by that first rule, then it's true for the sum. Is G omega n squared? So remember, omega n squared means that n squared needs to grow not as, needs to be below a lower bound for the function on the left. But remember, with omegas, we have that second rule where either only one, if we've got this sum here of two functions, so f plus g, either one or the other has to be omega of that in order for the sum to be. So let's look at g. Is either one of these, any of these terms, we've got 10 log n plus n factorial plus n squared. Do any of those grow faster than n squared? Because we're talking about omega, and that would, n squared would need to be below, at or below it. And yes, we've got this n factorial grows quicker than n squared, and not all of them are omega n squared, but only one of them has to be, based on this second rule. So we add those together and we get omega of h. I mean, sorry, we add those together and we know then that the sum would be omega of n squared. The last one, h, is h O of 1. Okay, so here we've got, in h, we've got two terms, both involving log. And let's take a look at where those are in the chart here. We've got log and then n log. So we see where they are in the chart. But then let's look at 1. Where is the constant function here? The one, some constant function. Where is that? That's at the very top. So being at the top means that it grows less quickly, right? So 1 grows less quickly than any of the others. So the question would be, is h O of 1? Well, no, because 1, if h is O of 1, 1 would have to grow more quickly, at least a constant times that, a multiple of that would have to eventually overtake these. But that doesn't happen. These do eventually overtake a constant, that they end up growing quicker. So we would have to say no, that's not true. Now this participation function here, I want to just briefly talk about it here. They don't really talk about what they're doing and why they're saying all of this, but I wanted to just give you just kind of a little rule of thumb. Eventually, if you look down here at the bottom, they're showing that this function here is theta of 2 to the n. Now, how would they have known to try to show this? That's the question. And if you take a look at these three terms, you see that the term that grows the most quickly, again, you might have to refer to this chart. The term that grows most quickly is this third one, 5 times 2 to the n. So that is almost down to the very bottom of this chart. It grows the most quickly. Well, here's this rule of thumb. It turns out that if you've got some different terms here, then the term that grows more quickly ends up overtaking, as we get bigger and bigger with our n values, that term ends up overtaking the others, and basically those others just are kind of along for the ride, but it really dominates. The one that grows more quickly is the one that dominates, and the whole function itself ends up just acting like that one that's the more quicker growing. So that's why they looked at this and found the term that grows most quickly, and then wanted to prove then that that whole function is theta of what was in that term that grew most quickly, which is 2 to the n. So that's where they were going with that, and that's how they're getting, why they're trying to show that that function is theta 2 to the n. So what they do is they look at each, first of all, they look at each term in f and show that each term is O of 2 to the n. And so then they're able to show to show this, and you'll have to look at that and try to figure out what they're using these rules over up here on the right. But they show this here, that f is O of 2 to the n. And then they show that that f is omega 2 to the n. And so once they're able to show that, they can show that the whole function is theta 2 to the n. So that's what they're doing in that participation. Hopefully by having looked at that, and you know why they were headed that way and how they would have known what the order of that function was to begin with in order to try to prove it, that's how they would have known.